Okay, good evening. This is ProfDavidJDelosReyes. Okay, it's September 5, 2023. The time is around 10:18 p.m. Okay, my topic for this session will be a long video format discussion on this is college algebra. We are almost done with the college algebra. Okay, let's proceed. The topic for tonight will be college algebra. This is lesson number 53. This is now 53. So we are running smooth, 53. We are almost done with college algebra. And the title of the topic will be geometric sequence concepts. Okay, the last time around we discussed arithmetic sequence concepts. I discussed how the concepts work. We give you example problems. So for tonight, I will be discussing geometric sequence concepts. Okay, it's like this. For a sequence to be called geometric, okay, this is the so-called definition. The ratio of the consecutive terms are equal. If we are given the geometric sequence A1, A2, A3, up to E sub n, for this sequence to be called geometric sequence, okay, according to the definition, the ratio of the second term over the first term will be equal to the ratio of the third term over the second term. So meaning to say, for the sequence to be called geometric, if we take the ratio A2 over A1, this should be equal to A3 over A2. Okay? And this should be, we'll just increase the number, A4 over A3. And this should be E5 over A4. Okay? And so on. Right? The ratios of all of these, okay, for it to be called geometric sequence, they should be equal. They should be equal. Okay, that's the definition of a geometric sequence. Okay, where R is actually the so-called common ratio. The difference between arithmetic sequence and geometric is that in the arithmetic sequence, there was a difference, okay? There's a gap in between the terms. And for the geometric sequence, okay, the ratios are actually the same. Meaning A2 over A1 is equal to A3 over A2. This is equal to A4 over A3. This is A5 over A4. And so on. And the name for R is actually the so-called common ratio. So if we hear a common ratio, okay, the subject matter should fall under geometric sequence or geometric progression. Okay, let's try to bring out the formula and how to compute for the nth term of a geometric sequence. Because if we got a geometric sequence, okay, there could be so many, what they call these numbers coming out, right? There could be 50, 100, and under the so-called IQ exams, they are giving this, what will be the, what they call this, the 100 term, if we are given the geometric sequence 1, 2, 3, something like that. So we shall now bring out the formula and how to compute for the nth term for a geometric sequence. So nth term of a geometric sequence or geometric progression, A sub n, small letter a with the subscript n, this should be equal to small a with the subscript 1 times r raised to n minus 1. This should be the formula. Okay? Where e sub n is actually the nth term and r is the common ratio, considering a geometric sequence numbers. So this will not be applicable to arithmetic sequence. This formula is only used for geometric sequence. Okay, let's try to bring out the formula and how to take the sum. We are given the numbers A1, A2, A3, there come a time that the professor, or what you call this, MC on an IQ exam may be asking what will be the sum of these so many terms, right? So under the study of the so-called geometric sequence concepts, there is a formula on how to take the sum. And this is designated by capital letter S. Am I still in camera? Capital letter S with the subscript N, and this should be equal to A1, the first term, times open bracket, 1 minus R raised to the N power over 1 minus R, close bracket. This is the formula on how to compute for the value of the sum of n terms. Where S, capital letter S with the subscript N, meaning the sum, and R is actually the common ratio. Okay, later on, we could visualize this formula as soon as we go to an example problem. But at this moment, I will just give you the formula on how to take the n term and the sum of n terms. This should be the formula on how to take the n term, and this should be the formula on how to take the sum of n term. If we are given A1, okay, we could compute for R, and n should be specified. Okay, so as always in algebra or in engineering or under mathematics, we always use a formula. Okay, that's actually our tools on how to bring out the solution of our problems. I think the formula on how to take the sum was derived by using the sigma notation. Okay, the summation with the limit from 1 to n of the given expression A1 times R raised to n minus 1. If we try to expand this, okay, and we try to simplify, we could bring out this equation here. Okay, so if we try to expand this one by using the sigma notation, okay, meaning to say the value of n, the value of n should be from value 1 to n, right? Okay, so for this in here, we will place the value from 1 to n, considering this expression to bring out the summation of a geometric sequence. So if we try to expand this one, it will be A1 times R. When n is 1, this should be 1 minus 1. Next one, A1R. When n is 2, the power of R will be 2 minus 1. Next one, this should be 3 minus 1. Okay, plus dot. Second to the last, it should be A1 times R raised to n minus 1. That is second to the last. And the last one will be A1 times R raised to the n power. Okay, if we try to simplify this one, R raised to 1 minus 1 is actually 0, right? So this will become 0. And R to the 0 is actually 1. So this is times 1. So the first one will be A1 times 1, or will just be simply A1. Next one, 2 minus 1 will just be simply 1, or just simply R. So the simplification of the second term is actually A1 times R. Right? Third one, 2 minus 1. So it will be A1 square. Okay, this will become square. Right? Plus dot, the second to the last, it will be A1, okay, raised to n minus 1. Last one will be A1 raised to R over n. And we try to, what you call this, bring out the common terms for all the terms. There is a common term A1, right? So we bring it out, okay, times open bracket. So if we brought out A1, what remains for the first term inside will just be simply 1. Right? Next one will be, we remove A1 here. It will just be simply R. R square. R cube. Okay? Second to the last, that will be R raised to n minus 1. The last one will be r raised to n, close bracket. Okay? And I think if we try to simplify this one, from our textbook, it was given that the simplified equivalent of this is actually this one here. Right? So if this expansion is equivalent to we brought out A1 already, right? So this A1, the simplified equivalent of this, I think it will be by using a long division or a synthetic division, okay? If we try to manipulate this one, this should be equivalent to 1 minus r to the n over 1 minus r. So the general formula on how to take the sum of a geometric sequence will be A1 times the quantity 1 minus r to the n over 1 minus r. It is this. Right? The given condition for the sum of the geometric sequence is that this is just for the so-called real values, you know. It should be values greater, meaning to say the ratio is actually greater than 1. Greater than 1 for this equation here. Okay. Okay, let's try to bring out the formula on how to take the sum of infinite geometric series. Infinite meaning up to infinity maybe. That's why it's infinite, right? Up to 1,000,000 times, maybe 1,000 times, 1,000,000,000,000 times. If we try to take the sum of an infinite geometric series, what will be the result? We will start from here. For infinite geometric series, there is a condition for this. The value of r is less than 1. Okay, it should be less than 1. 0.001, something like that, 1/2, 1/3. Okay, so if the ratio that comes out is less than 1, we will be using this formula here. And to derive this formula, actually this formula here was derived from the geometric series in which the value of r is greater than 1. So under infinite series, okay, the formula will be S with the subscript A should be equal to A1, I'm following this one, times the quantity 1 minus r to the n over 1 minus r. But if r is very small, okay, the resulting equation will be A1 times the quantity open bracket 1 minus, this small here will be a small number, okay, maybe 0.001 raised to 1,000 times, right, all over 1 minus r. Whether we like it or not, if the number inside is very small, raised to a very high value, whether we like it or not, the value is almost approximately equal to 0. Right? I will give you an example like a less than 1, right? A 0.2. We raise this to 1,000 times. Okay? 1,000 times, 1,000 times. Okay? The value is 0. It's not 0, but it's almost 0. So meaning to say, if the value of r is very small and we raise that to an infinite number, meaning a very big number, whether we like it or not, the value of that small number raised to a big number will be 0. So from the given equation, if this is a small number raised to a very big number, this will disappear. Right? Because this will become 0. So if we try to simplify the equation, it will be, if this is 0, we could remove this one now, okay? So the 1 on the numerator inside the bracket will just be simply 1. So A1 times 1 will be A1. The resulting denominator will just be simply 1 minus r. And this is the formula on how to take the summation of a geometric series if the value of r is less than 1. It is this formula. It is simpler than this one. Okay? The first equation is actually longer because what will come out for the solution will be a real thing. We could still bring it out on the calculator, the value r to the n. But under the so-called infinite geometric series, the value r to the n, if r is very small, okay, whether we like it or not, it will be almost approximately equal to 0. So the resulting equation for infinite series summation will just be simply a1 all over 1 minus r, and that's it. Okay, this is simpler than the real value in which the value of r is greater than 1. But for r which has a value less than 1, okay, this value here will disappear. Okay, it will just be simply a1 over 1 minus r. Okay, that's the derivation of the so-called summation of infinite geometric series. That is when the value of r is less than 1. Okay? Okay, let's try to bring out an example, okay, to visualize the different formulas under geometric sequence. There are only 3 formulas for computing the value of the enter, for taking the summation of a geometric sequence, that is when r is greater than 1, and the third one is actually the formula on how to take the sum of a geometric series if the value of r is less than 1. Okay, it should be this formula here. So there are only 3 formulas which must be memorized under geometric sequence. Okay, let's try to bring out an example problem. Find the 22nd term of the geometric sequence. We are given a geometric sequence. First one is 2, next one is negative 10, third one is 50, the fourth one is negative 250. And we are to take the 22nd term. Okay? Actually, we could bring out the 22nd term by using brute force. Okay? You just write it, then you try to keep multiplying this one until 22 times. Right? Because there should be a ratio that will come out here. Okay, let's try to bring out the solution. The value of a1 will be 2. The value of a2 will be negative, then is negative. The value of a3 is positive 50. And the value of a4 is negative 250. For this one to be under geometric sequence, let's try to verify, because under geometric sequence, the ratio of a2 over a1 should be equal to the ratio of a3 over a2, should be equal to the ratio a4 over a3. Okay, verification. R will be, a2 is negative 10, a1 is 2. Okay, what is negative 10 over 2? That's negative 5. Right? Next one. We try to verify if this R is actually same for all the succeeding terms. The third term is 50. The second term is negative 10. And 50 over negative 10 is still a negative 5. So it's still true. Right? Last one. The fourth one is negative 250. The third term is 50. Negative 250 over 50 is still a negative 5. So as per verification, we brought out 3 solutions and they are all the same. So we could say that the given series is actually under geometric sequence. Okay? And the problem is only asking for the 22nd term. So n here should be equal to 22. What formula we will be using? It will be formula number 1. That is, e sub n will be equal to e sub 1 times r raised to n minus 1. So, computing for the 22nd term, a 22nd now should be equal to a1, which is 2. The value of r as per verification is negative 5. Carry the sign, okay? Raised to n minus 1. N minus 1 is actually 21, right? So this is raised to the 21. 2 times the quantity negative 5 to the 21. That's a very big number. The power here is 21, right? And this is negative. So if we try to raise this one to the 21 power, okay, it should have a negative value. It should be preceded by a negative sign. So actually, the overall sign of the 22nd term is actually a negative value. And it's a very big number because the ratio is times 5, negative 5, right? Or if we try to calculate this one, I will just display negative 5. The power is 21, right? Y to the x, 21. This is a very, very big number. Negative 4.768 times 10 to the 14. 10 to the 14. It's more than a trillion, right? Because a trillion is just 10 to the 9, and this is 10 to the 14, right? So if we try to multiply this by 2 times 2 equals the approximate the value of this 22nd term, considering this geometric sequence, it should be negative 9.536 times 10 to the 14. Okay? So it seems trillion is 10 to the 9th, right? 536 trillion. Okay, because this trillion is 10 to the 9. We got 5 over already here, 10 to the 5. 10 to the 5, 10 to the 9 is actually 10 to the 14. So the answer here, the 22nd term for the given geometric sequence is actually 95,360 trillion. We could verify this one by using our calculator. We'll just start with this a sub 4 is negative 250, right? And the ratio is always times 5. So if you try to multiply this by 5, succeeding up to the 22nd term, okay, what will come out is this. Okay, I checked this already by using the calculator. Okay, I start with negative 250. Negative 250 is actually the fourth term. So if I will try to multiply this by negative 5, right, that will be the fifth term. Then again multiplied by 5. Then multiplied by 5 up to the 22nd term. What will come out will be negative 9.536 times 10 to the 14. I checked this using the calculator already. Last example for tonight. Find the sum of the first 7 terms of the geometric series. The geometric series is, I'm checking my camera. Oh, it's still time. The geometric series is 118. Second term is negative 16. Third term is 1/2. And the problem is asking up to the 7 terms, what will be the summation? I checked this also by using the calculator, but I will not place it here. Anyway, I checked it already by using the calculator. So A1 here is 1 over 18. A2 is negative 16. I still in camera. And A3 is 1/2. For this one to be under geometric series, let's try to, what you call this, verify the ratio. A2 over A1 will be negative 16 over 118. This should be negative 16 times 18 over 1. We change the operation from division to multiplication. Negative 16 times 18 over 1 will be, the ratio is actually negative 3. Actually, we could bring out a third solution. The ratio R is still 1/2 A3 divided by A2. Negative 16. So this should be 1/2 times negative 6 over 1. We change the operation from division to multiplication. We invert the value of the denominator. So this should now be multiplied by negative 6 over 1. And negative 6 over 2 is actually equal to negative 3. So this is negative 3, this is negative 3. So as per two verifications, the common ratio for this geometric series is actually negative 3. And to take the sum up to the 7 terms, okay, we will be using the second equation. The absolute value of R is actually, okay, greater than 1. The absolute value. The value of R, we should take the absolute value. If the value of R is greater than 1, we will use equation number 2. Okay? So this will not be under infinite series. This should be under the so-called, we could bring out the value using the calculator. If the value r to the n could be computed by the calculator, there's no problem, okay? That's why we will use equation number 2. So, using equation number 2, but carry the proper sign. So, they should be a1 times quantity 1 minus r to the n over 1 minus r, the one we derive. So, a1 is 1 over 18 times open bracket 1 minus, the value of r is actually negative 3, right? Raised to the 7th power, the value of n is 7. The problem is asking for the summation up to the 7th term. So the value of n will be 7 all over 1 minus open quantity minus 3. Carry the proper sign. If we try to calculate negative 3 to the 7, okay, this is negative, right? We raise that to the 7th power, so it should be a negative. What will come out for the sign of this will be negative. But since this is preceded by negative sign, it will now be added to 1. So what comes out will be 3y to the x 7 equals 2187. But we will add 1 plus 1. So 2188. So the numerator will be 2188 and the denominator will be 1 minus 3, that will be positive 4. And if we try to, the answer is not exact. 2188 divided by 4 equals, again divided by 18. It's 30.388, or this should be 30.39. Okay? And again, as you check, I used the calculator a while ago, okay? I take this 1/8 minus 1/16 plus 1/2 plus the 4 succeeding terms over here, carrying the proper sign, okay? What comes out is 30.39. Oh, that's only the verification that we could bring out to check the validity of this answer. Okay, that's it, guys. That's geometric progression or series or sequence. They are all the same. That's the concepts and example problems under the subject matter geometric sequence concepts. Okay, this is Professor David J. Delos Reyes from Los Angeles. Good evening.